Hello everyone, welcome to Explore Electronics. In this video, let's see 2 to 4 decoder, truth table logic circuit, and also let's write the data flow description and behavioral description code in Verilog. 2 to 4 decoder will be having two inputs. I have taken it as AB and four outputs Y3, Y2, Y1, Y0. As the name says, it is 2:4 decoder, means it is taking an encoded version of the inputs, that is AB, and it is decoding that to 4-bit output, that is Y3, Y2, Y1, Y0. Here, to control the operation of this decoder, we have an enable signal. This enable signal is active high signal. When enable is 1, this decoder is going to function the decoding operation. If you look at the truth table here, you can see enable is equal to 0 and AB is XX, means irrespective of AB, whatever the value of AB, outputs will be 0, 0, 0, 0. Means when enable is equal to 0, you can't expect the decoder to decode the inputs to get desired output. So output will be 0, any of the input AB comes when enable is equal to 0. When enable is equal to 1, if the input are 0, 0, it will be decoded to 4-bit value as 0, 0, 0, 1. And when the input is 0, 1, it is decoded as 0, 0, 1, 0. Similarly, for 1, 0 input, it is decoded as 0, 1, 0, 0. Similarly, for 1, 1, it is 1, 0, 0. You may have a different decoded output sometimes. Depending on the necessity of the decoder, this decoding output will be decided. For 0, 0, it might be 1, 1, 1, 0 or 1, 1, 0, 0, like that. So here the 2-bit input will be decoded to a 4-bit value. That is what we need to understand. So for this truth table, if we write the logical expression for Y0, Y1, Y2, Y3, it is enable into A into B. So to get Y0, enable, you can see here, for this Y0 is equal to 1, enable is 1, A is 0, B is 0, so it is A bar, B bar. Similarly for Y1, we need to have enable and with A bar and with B. Similarly for Y2, enable into A into B bar. Similarly for Y3, it is enable into A into B. So if we write the logical circuit, it looks like this. It requires 4 AND gates with 3 inputs, and to generate A bar, B bar, I am using these two NOT gates and with an enable signal like this. So this is the circuit for decoder for this functionality. Whatever the functionality I have taken here at the truth table, for that, this is the circuit. And let us write the Verilog code. First, let us write in data flow modeling. As we know, in data flow modeling, we are going to use these expressions, logical expressions, and looking at the logical expressions, we are going to write the code. So first, Verilog code start with module and then name of the module, and here the input and output ports are enable A, B, and Y is the output. So let us declare inputs enable A, B, all are single bit, and let us declare outputs. Output is, here I have taken it as a vector 3:0 Y. So it gives Y0, Y1, Y2, Y3. And we need to use assign keyword since I am writing it in a data flow description style or data flow modeling. So for Y0, assign Y of 0 is equal to enable, that is En, and with not of A and not of B. Similarly, assign Y1 is equal to the same expression by using operators, AND operator and NOT operator. It is a very simple Verilog code for 2 to 4 decoder. And finally, after all 4 assigned statements, we need to end with end module. This is how data flow modeling Verilog code will be. And if we write the same using behavioral modeling, you can see here, we need to use the output as register. So here the output Y need to be represented as reg, means it will store the output value. All the time when you are going to write a behavioral modeling style code, you need to write the output as register. And we need to use always statement here in the behavioral modeling. Always at the rate, within the brackets I am going to use enable A and B. Why? Because this decoder output will be sensitive to change in enable A and also B. So this will be called as a sensitivity list. Here we need to include all the sensitive parameters for this design. And then it will be start with a begin. Then we need to use a case statement here, or else we can use if else statement. So I am going to write this code using if else statement. First I am going to check if enable is equal to 1. So while explaining also I said depending on enable, then we need to look for what is AB. First thing is that enable should be 1. So I am checking if enable double equals 1, means it is checking for enable is 1 or not. If it is 1, it will entering into the begin now. Now if next condition it is checking is that A double equal to 0 and with B double equal to 0, means it is checking for A0, B0. If this condition is true, Y is equal to 4 tick B 0 0 0 1. If A is equal to 0 and B is equal to 1, Y will be this. Similarly, else if A is equal to 1 and B is equal to 0, Y is this. Else if A is equal to 1, B is equal to 1, this is the output. So here it is checking for 0 0 first, and then 0 1, then 1 0, then 1 1. Finally, after this 4 statements for enable is equal to 1, then we are going to write this. Else Y is equal to x x x x. Here we can write 0. Here in the code I am using it as, I am writing it as x x x x. In place of that you can write it as 0 according to the truth table. But here it is mentioned it as x. And finally we need to end this always block with the end and end module. This completes the behavioral modeling code for 2 to 4 decoder. So what you can do is that you can write the behavioral modeling code using case statement. I have already explained in other video how to use case statement for 4:1 multiplexer and 2:1 multiplexer. In the similar way, here also for the 2 to 4 decoder you can use case statement. You can try it out. And also you can simulate this to get the waveforms as I explained in the previous video.